Alright, so let's talk about what is the common mode voltage produced by a voltage source converter, right? Because that is one of the forcing function for the flow of common mode current or the leakage current in case of solar PV systems. So, so the analysis we are going to do now, we are going to do it on a full bridge inverter as we have done in the previous video also. But whatever we are doing now in this particular video can be applied to any other circuit topologies as well, right? So it's a more generalized way of analyzing the common mode currents or the common mode voltages in a PV system. So let us consider a full bridge inverter which is S1, S2, S3 and S4, right? And now they are connected through inductors to the grid, right? Now if you remember in the last video we assumed that both inductor values are same. Here let us be a little bit more generalized. Let's say there is L1 and L2, right? And in some of the cases, for example, you may take L2 equal to 0, then it would only be L1. So now I'm considering L1 and L2 two separate parameters so that it can be set equal or it can be not necessarily be set equal also. Let's consider some more non-aridity. For example, let us say when you are earthing, there is a earth resistance Rg, right? At substation when you are earthing the neutral, there is a earth resistance Rg. Let this point be A and B. On the DC side, as we have already seen, right, there is we can assume the DC voltage to be almost stiff because of the large capacitance that we usually include on the DC bus. And then there is parasitic capacitance CP1, which is connected between the negative bus and the earth, and another parasitic capacitance CP2, which is connected between positive bus and the earth. So this is the architecture, right? Let's say alpha of t is the switching function, implies when alpha is equal to 1, when alpha equal to 0 implies S1 is off, and while alpha is equal to 1, S1 is on. Obviously S1 and S4 are complementary, so S1 off means S4 is on, and S1 on means S4 is off. Similarly, beta of t as the switching function for the other switching function is also switching function for S3, right? And therefore beta is equal to 0 implies S3 is off and S2 is on, and beta equal to 1 implies S3 is on and S2 is off, right? So by S1, by alpha and beta, right, by using these two, we can define the state of the inverter switches. Let's move ahead now. Let me just create some more space here. So now I will try to define the voltage. Let me call this point here as maybe C point, right? So let me define VAC. VAC is nothing but VDC into alpha, right, or alpha of t. So if alpha of t is 1, that means S1 is on, that means VAC is equal to VDC. If alpha is 0, that means S1 is off and S4 is on, right? In that case, VAC is equal to 0. Similarly, I can define VBC as VDC into beta of t. So you see I have defined VA with respect to C and also V with respect to C. So now I can redraw the above circuit something like this. I can replace these switching network instead of two voltage sources VSC and VBC. So on the DC side we have VDC, right? Then there is a point C, there is capacitor CP1 connected to earth, and then from the positive side there is another capacitance CP2 connected to earth. From this point C you can see that there are two voltage sources, VAC and VBC, followed by inductors L1, L2, by the grid VG, and then through a resistance RG to the ground. This is the equivalent circuit of the above inverter. Right, so far so good. Now as we understand, we are worried about, or rather we want to study the current that is flowing in the ground, right? So I leakage. Now I leakage in this circuit, if I see there are 1, 2, 3, 4, there are 4 sources, right? So it is going to be a combination, or would be contributed because of all 4 sources in one way or the other, right? So to analyze that, we can use superposition and then see the effect of each of those 4 sources. So let's use superposition, right? First let us only consider VDC, right? So let us make all the other sources 0. In that case, the equivalent circuit would look something like this. There's a VDC, and then there is the cap CP1, CP2, and these two are 0, so it is L1 in parallel to L2, and grid voltage is also 0, RG going to earth. So now if you solve for this circuit and you try to find out I leakage due to VDC, right, what you will get is 0, because at steady state this is a DC source, right, and the capacitors will get charged to suitable DC values, and there will be no DC current flowing through these caps. If there's no DC current flowing through either of the caps, then the circuit cannot complete, and there cannot be any leakage current also, right, if there's no current from these caps. So the DC source does not produce any leakage current as such, right? Now just a caution here, the leakage current does depend on the magnitude of VDC, right, which you will see, but it does not depend on the DC source. The reason is that these VAC and VBCs, right, these two voltage sources are also, VAC and VBC is also a function of VDC, and these are the two sources which actually leads to the leakage current and making it a function of VDC, right? So yes, leakage current is a function of VDC, but the leakage current because of this particular source shown in this figure is 0. Alright, now let's continue applying superposition. So now let us say we apply superposition and we make V grid not equal to 0 and all the other sources equal to 0. In that case, the equivalent circuit would look something like this. So if DC voltage is 0, then both the caps will come in parallel. So this is CP1 plus CP2, right, and then put the inductors in parallel, L1, L2, sorry, not inductors are not in parallel, so L1 connected to VG and then through resistance to ground. This is the equivalent circuit if you consider grid voltage as non-zero and the other sources as 0. So now if you see this circuit here, in a way there is going to be low frequency current that will flow in this circuit because of VG, right? There is going to be current which will flow because of VG through the ground. But as we discuss, the impedance offered by the capacitor, right, at low frequency, low value of C, and you have low value of omega, and you also have low value of capacitance, and therefore this is usually large for grid frequency, and therefore this will produce some leakage current, but this is going to be small. Right, so far so good. So we have analyzed two sources, and we have seen that one of the source does not produce any leakage current, the other source does produce a leakage current, but we expect the value to be small. If you want to find the exact value, you can do the analysis and you can find it out, right? In fact, if I just redraw the circuit in a little bit different way, then you would realize what is the meaning of common mode voltage. So this is, if I only redraw L1, L2 and VG, right? This is how it looks like. And there is capacitance here, and this is returning through ground, right? Now I can draw the Thevenin equivalent of this block, right? So what is the Thevenin impedance? Thevenin impedance is going to be L1, or rather ZL1 in parallel to ZL2, right? So Thevenin equivalent is going to be equal to SL1 SL2. If I write in Laplace, then SL1 plus SL2, right? And what is the Thevenin voltage? Thevenin voltage is going to be equal to VG on SL1 plus SL2 into SL2, right? So if I redraw this circuit here, then you can see that I can redraw it as an inductor, which is L1 L2 upon L1 plus L2, which is essentially the parallel combination, and a voltage source which is given by VG into L2 upon L1 plus L2. Let me just say it's Cp, which is the combination of the total capacitance because of all the panels, right? So what is this circuit? This circuit, we can call it as a common mode equivalent circuit. Why so? Because it can give us the common mode current that flows in the circuit, and this particular voltage source, we can call it as a common mode voltage source due to grid, right? Because this is a common mode voltage that is being applied because of the grid being present. So you can see here, if L2 is equal to 0, right? So if I go above and I show you the original circuit, right? If L2 is 0, right, in that case there is going to be no low frequency current that will flow in this circuit. Vg into L2 upon L1 plus L2 is equal to 0 implies I leakage due to the grid voltage is equal to 0, right? So yes, usually if you do not put L2, it is good in a sense that it would suppress the leakage current due to grid, but as we will see shortly, it does not suppress, or it rather does not optimally suppresses the leakage current due to the inverter voltages, and therefore usually you would keep L1 is equal to L2 rather than L2 being equal to 0, right? So even if L2 is not 0, we understand that I leakage Vg is going to be small, right? Because the capacitance value is small and the frequency is also low of this circuit. All right, let's move ahead now. Let us see the third scenario. So we have already considered scenario 1 where only VDC is present, scenario 2 where only VG is present, third scenario where both of them are 0, only the inverter voltages, which is VSC and VBC, are present. So let us let us work on this third scenario now. We copy this circuit. Yeah, third scenario where VAC and VBC, which are produced because of the inverter switching, are non-zero. So how would the equivalent circuit look like? The equivalent circuit would be VDC is 0. So again, both capacitor will come in parallel and they will, let me call it as CP, which is the addition of all the capacitor on the parasitic capacitance because of the panel. And then there is source VSC, there's another source VBC, inductance is L1, L2, this is short because grid voltage is not there, and RG connected to the ground. Again, we can do the same thing. We can find the Thevenin equivalent of this, right? In that Thevenin equivalent, we can replace and show that equivalent circuit. So let me do that. Left side, I have a CP. Then let's say I have an equivalent AC and the equivalent inductance followed by RG connected to the grid. Right, what are the values? The L is same, it is the parallel combination of the two. So this is L1 L2 upon L1 plus L2. And if you find this, let me call it as V inverter common mode, right? So what is V inverter common mode? If you try to find V inverter common mode from the analysis, then you would get L1 into VAC plus L2 into VBC upon L1 plus L2. Right, sorry, I think there is some mistake. This should be L2, right, and this one should be equal to L1. Yeah, all right, so this is the common mode voltage induced or common mode voltage introduced in the circuit because of the inverter switching, right? Because of the inverter switching. Now VAC and VBC we have already found above, and we can just replace. If I'll just scroll above and show you so VAC was alpha times VDC and VBC was beta times VDC. Right? So I can just substitute it here. And I can write that L2 into alpha plus L1 into beta of T upon L2 plus L1 whole thing multiplied by VDC. Right? This is the VDC I was referring to some time back. So you see the inverter induced, or rather the inverter injected common mode voltage is also a function of VDC. And therefore the leakage current is a function of VDC. So this is, let's say, the leakage current, I leakage due to inverter common mode voltage, right? This is the inverter common mode voltage. Okay, now let us consider the case of unipolar modulation for the time being, or rather bipolar modulation, right? So if it's a bipolar modulation, we understand that when alpha is equal to 1, right, that let me draw the switches here. So when alpha is equal to 1, then beta is equal to 0 and the output state VAB is equal to VDC, right? And when alpha is equal to 0, then beta is 1 and VAB is equal to minus VDC. It never happens that both of them are 0 or 1. And now if I substitute this thing here, then you can see that the inverter voltage, if in the first scenario, the inverter common mode voltage will be equal to L2 upon L2 plus L1 into VDC. And in the second case, this common mode voltage will be equal to L1 upon L2 plus L1 into VDC. And therefore, if you remember, I said that if you keep L1 is equal to L2, implies that both these expressions will be equal, which is this expression will also be equal to VDC by 2, this expression will also be equal to VDC by 2. And thus, when you are switching between these two states, the inverter common mode voltage remains constant. That means the inverter common mode voltage is nothing but equal to the DC value, right? And therefore, there is no leakage current because of the switching action. But if you do not keep L1 is equal to L2, even in bipolar modulation, we will have leakage current, right? So if you can see that if L1 is slightly not equal to L2, right, then the left hand side expression and the right hand side expressions are no longer going to be equal, right? And if they are not equal, that means as the inverter is switching, the inverter common mode voltage is switching between these two values. That means the inverter common mode has a high frequency component which will produce high frequency current. Obviously, if the error between L1 and L2 is very, very small, then this high frequency component is going to be very, very small. But if one of them is 0, then you can imagine that there is going to be a significant amount of high frequency current that will flow. That is the reason usually we like to keep L1 is equal to L2, or rather we like to divide the total inductance between the phase and the neutral, and not only put all of them in the phase. So this was about bipolar. You can see what happens in unipolar for yourself, right? Unipolar, you can now have independent, so alpha could be equal to 1, beta could be equal to 0, alpha equal to 0, beta equal to 1, right? Or alpha equal to 0, beta equal to 0, and alpha equal to 1, beta equal to 1, right? So you would use, let's say, switching between this one and one of these two states. So you can find the common mode voltage in the two scenarios, and you can see if the common mode voltage remains constant or it is a function of switching frequency, or it is varying with the switching frequency. So you would, if you do this analysis, you will find the common mode voltage is a function of switching frequency in the case of unipolar, and therefore there is a leakage current. So this analysis in a way converges and gives us the same conclusion as we have done in the previous video 5.2. The only difference is this is in 5.2 it was a much simplified analysis. The inductance values was considered equal, there was no grid, there was no earth resistance considered, and so on. This analysis is a little bit more detailed, and in fact going forward, because this is going by the first principle, you can include lot more other non-ideal factors here. Just to give an example, let's say what if there's a transformer in the circuit, right? You can just include this transformer in this circuit and analyze for common mode current. What if the switch, right, the switches which are getting turned on and off forms a capacitance with the heat sink? What will happen to the common mode currents now? Again, you go by the same approach, and you can consider those capacitances in the circuit, and you can analyze those capacitances also, right? So this generic approach of defining the common mode voltages because of different elements, because of the inverter, because of the grid, and so on, helps us analyze the circuit, helps us find out the leakage current and the contribution of the different sources and the different phenomena on the leakage current. So moving forward, now what we will do is we will try to understand some more circuit topologies, or rather some more methods of how to avoid the flow of leakage current in solar inverters. And while doing so, we would be using this equivalent circuit or this kind of equivalent circuit to understand the common mode voltages appearing and how it is leading to the leakage current.